Okay, in this tutorial we're looking at section 10.5, which is on arc length, numerical integration and graphs of antiderivatives. Hey, the length of a curve f of x between 2 points a and b where a is less than b is given by s equals the integral from a to b of the square root of 1 plus the derivative of f of x squared dx. Okay, so it's a nice little equation there that we can use. Our numerical integration. Okay, often we need to integrate functions which are too difficult for us to tackle or simply can't be done. Okay, however, there are techniques which approximate the integral. Thankfully, our calculator can do the work for us. And the tip here is if the question asks for an answer to a specific number of decimal places, we can simply use our calculator. However, often we can't simply put our function into our calculator. We need to do some work first. Okay, if we have dy dx equals f of x, where y of x naught equals y naught, and we want to find the value of y1 when x equals x1, okay, then we use our function y1 equals y naught plus the integral from x naught to x1, f of t dt. Okay. When we start talking our graphs of antiderivatives, okay, this is something that shouldn't be completely new to us. We should have seen some of this in maths methods at some stage. Remember, capital F of x is our antiderivative. So if our original function, okay, its x-intercept will be a turning point for our antiderivative. Whenever it's above the x-axis, that means our antiderivative will have a positive gradient, or if we're below the x-axis, it'll have a negative gradient. Okay, a turning point that's not on the x-axis, okay, this is a non-stationary point of inflection. Our turning point on the x-axis is a stationary point of inflection. If we start off with a linear function, it'll go to a quadratic function. If we start with a quadratic, it'll go to a cubic. If we start with a cubic, it'll go to a quartic. Okay, pretty straightforward there. Okay, so we'll get into a couple of worked examples. So worked example 11, we want to find the length of the curve y equals x cubed on 2 plus 1 on 6x from x equals 1 to x equals 5. So what we need to do is we need to start off by finding our derivative. Okay, so we can say our dy dx, okay, is going to be equal to 3x squared on 2 minus 1 on 6x squared. Okay, so then we can use our equation. Okay, so we can say, well, s is equal to our integral from a to b of the square root of 1 plus dy dx squared dx. Okay, so that means that we're going to be from 1 to 5 of the square root of 1 plus 3x squared on 2 plus 1 on 6x squared squared dx. Okay, what we need to do is we need to expand our brackets out. So 1 to 5 square root of 1 plus, that'll be 3x squared on 2 squared minus 2 lots of 3x squared on 2 times by 1 on 6x squared plus, it'll be our 1 on 6x squared squared dx. Okay, so that goes down to integral from 1 to 5 of the square root of, we can simplify everything down, so we get 9x to the 4 on 4 plus a half plus 1 on 36x to the 4 dx. Okay. This is actually a perfect square. This part is. Okay, admittedly, probably good luck spotting that most of the time. That would be probably a pretty tricky one to realise it was a perfect square. Okay, but it is. It's actually 3x squared on 2 plus 1 on 6x squared squared dx. Okay, well our square root and our squared will cancel out, so we're now saying s is our integral from 1 to 5 of 3x squared on 2 plus 1 on 6x x squared dx. Okay, so again we can think of this as our s equals our integral from 1 to 5 of 3x squared on 2 plus 1 on 6x to the negative 2 dx. Okay, so when we integrate that, we're going to get x cubed on 2, take 1 on 6 x to the, to put the x down here, from 1 to 5, okay. And then we can sub our values in, so we can say our s then is equal to our 5 cubed on 2, take 1 on 6 times 5, take away 1 cubed on 2, take 1 on 6 times 1. Okay, and when we do our arithmetic on that, we end up getting 932 on 15 units long. Okay, so hardest part with that one was probably honestly the step down here, which was realising that was a perfect square. Okay, as I said, you should be going pretty well to realise that was a perfect square. Okay, so I mean it's just one of those things you need to keep an eye out for. Okay, and yeah, really just see how you go. We'll have a look at work example 13 now, okay, which is one of our ones on our numerical integration. So we've got, given that dy dx equals e to the x squared and y of 1 equals 2, find a definite integral for y in terms of x, and then we're going to determine the value of y correct to 4 decimal places when x equals 1.5. Okay, so we know that our dy dx equals e to say e of x squared. Okay, so using our formula that we had from earlier, we can say that we've got y equals an integral from 0 to x of e to the t squared dt plus c. Okay, is what we have. Okay, now what we need to do is substitute x equals 1 and y equals 2. So we have, well, 2 equals an integral from 0 to 1 of e to the t squared dt plus c. Well, that means c is going to equal 2 minus our integral from 0 to 1 of e of t squared dt. Okay, well, we can put this value back in there now and say, well, we've got y equals our integral from 0 to x e of t squared dt, okay, plus 2 minus our integral from 0 to 1 of e of t squared dt. Okay, we can just rearrange that a little bit. Okay, and say that it's 2 plus our integral from 0 to x of e of t squared dt. Okay, and what we can do is make this plus instead. Okay, from integral from 1 to 0 of e of t squared dt. Okay, and so what we can do when we've got this, when it looks like this, okay, what we can do is we can actually bring them together. Make our integral our 1 to x, so 2 plus our 1 to x e of t squared dt. Okay, so we've used a few steps there, okay, that we've ended up getting to our equation that we wanted. Okay, so we could have jumped straight to here using our formula, but thought I should show you the steps here. Okay, because this is our if we just flip back to our equation. Okay, this is our y1. Okay, this is our y. This is our y naught. This is our x naught. Okay, we can make this y1 by making this x1. Okay, which is what we're going to need to do in our next part. Okay, which is part B. So this is our answer for part A. So in part B, we actually know, we really say that's x1, and we want to find the value of y1 correct to 4 decimal places. So really, it becomes y1 equals 2 plus the integral from 1 to 1.5 of e of t squared dt. Okay, and when we plug that into our calculator, we find that our y1 is equal to 4.6005. Okay, so we'll keep moving along. We'll have a look at worked example 15. Okay, so we've got a couple of graphs that have been given to us. Okay, and we need to find a possible antiderivative graph. Now it says possible graph of the antiderivative. Okay, simply because we know when we find an antiderivative or we integrate, we have our constant of integration, that plus c. What that plus c does is basically translate our graph vertically. Okay, so we've got a function here. Okay, and we need to find our possible antiderivative. Okay, so what we need to think is, well, my x-intercept is going to be a turning point. Okay, we know we've got a turning point here. Okay, we know that our gradient on the left-hand side is positive because we're above the x-axis. Okay, our gradient of our new function will be negative to the right of it. Okay, so we've got to be positive, 0, negative. And we know that it's a linear graph. Okay, so our new function will be a quadratic. So I'm going to draw it here and say, well, that's my turning point there, and I simply come down like this. Okay. Now you'd be correct in doing that, okay, and putting this graph anywhere up here or down here. So you could draw it up here, you could draw it down here, it wouldn't matter, as long as your turning point's there, okay, then you're laughing. And that's because of that c value at the end when we integrate. Okay, that's what I was talking about when I mean that translation. Okay, so we'll have a look at the next one. Okay, so the next one we're given is a quadratic. Looks like this. Negative 3 there, and we're at negative 1, and we're at 3. Okay, so we're quadratic, so we know we're going to be a cubic. Okay, we know we're going to have turning points at -1 and 3. Our gradient over here has to be positive, so we think we're going to be positive gradient. Okay, then we're going to be 0, then we're going to be negative gradient. Okay, all the way through to down here somewhere, we're going to have our other turning point. Okay, then we're going to be positive gradient. Okay, so I'm going to say I've got my turning point here and my turning point, say, here. Okay, I also know that my stationary point, my non-stationary point of inflection will be in between here. It'll be there somewhere. And say up, down. Will be something like that. And again, of course, you can move this graph up and down, okay, because of the plus c. So we had our x-intercepts became our turning points. We used the idea that this was above the x-axis, the gradient was positive. This was below the x-axis, the gradient was negative. Okay, this was above, so our gradient is positive. Okay, and our turning point here was our non-stationary point of inflection. Okay, so I really don't think you'll have too many troubles with the graph parts. I think you'll really fly through those questions. You might just get a little bit bogged down in some of the other questions, but look, if you have a look at the worked examples and you follow those when you're attempting the questions, you shouldn't have too many dramas with these questions.